that's the ceramics, and I've never stopped dealing with ceramics. I study them every day, bring them in. It's never stopped in 34 years. So we will develop new coatings later on based on what we already know. Okay, I'm Joseph E. Pritchett, but I go by J.E. I'm the owner-founder of Superior Products International, and started in about 1987, the latter part. And I got interested in reflective coatings at the time. And in that whole concept of reflective coatings, when I first heard about it, it was called ceramic, and I thought, well, that's interesting. What is a ceramic? But it's okay, it reflects heat and it does this great job. Well, I had been in retail advertising and all that for about 19 years, so I did my research and found probably the best reflective coating in the market at the time. And that was happened to be down in Texas. So I got a hold of these people, went out to a trade show, saw the information that they had, thought, well, this is just fantastic. And so I thought, well, I'll set up a company and I'll start selling this for them. And so I did. And within about 6 months, I'm down in Mexico and different places, major corporations, and they're kind of asking me, well, you said it would waterproof and it would just throw the heat right off and all this kind of stuff, and it's really not doing it. And so me as the salesman right there, I'm looking at them and I'm looking at the plate they're talking about and the application, and I'm thinking, you're right, it's not working like we said. And I said, now that's a key element in the whole progression of Superior Products. Because at that point, I'm like, okay, there's got to be truth in advertisement, because I'm the guy face to face with the customer, and look, it's got to work, like I said, for me to stand there and sell it. And you got to believe in it in order to sell something. So I talked to the guys that manufactured it at the time, and they said, well, yeah, no, this is how we got this. We kind of bought the formula from this one guy that developed this, and this is the best there is. And I thought, well, that doesn't mean anything. It still doesn't work. So I happened to have an uncle that worked for NASA at the Redstone Arsenal in Huntsville, Alabama. So I called him. And now I'm a salesman, you know, out of retail, things like this, and I don't know beans about ceramics, but I'm about to find out. So I call him up and I say, I need to talk to the guys who make the tiles for the shuttle, thinking he had a direct connection or something and they would know everything. So he put me in touch. I went and talked to him. And I said, in discussion, I told him what I was trying to do. And I said, do y'all have a coating? No. But you have ceramics that you use on the tiles and things? Yeah, sure. And I said, well, would those work in a coating? No, because you got to take those and put it in a high heat situation, make a tile, and then you glue it to the shuttle and yada yada. And I thought, okay, well, do you have a ceramic book? Absolutely. And I said, so they said, well, here's the top 17 ceramic compounds in the book as far as heat transfer coming in on this side, going through the product or the material and exiting the other side. Great. So these 17, I ought to find some in there that's going to work. Absolutely. Okay. So they said, well, you'll have to do this in your lab, which at the time was my garage. And I said, okay. So they helped me get the compounds. And then I came up with just this white paint stuff and put it on a piece of metal plate. Found out that you had this lamp sitting about 6 inches away at a certain wattage. It would put the same heat onto that metal as a 90 or 38 C day would on a metal surface, like a roof. And so, okay, now I've got the piece of metal, light on it. How much heat came through the back side? Okay, now put that white paint on there. Heat, how much heat came through on the back side? Practically the same amount. White paint, I don't care what the testing all says out there, like a 70% reflectivity, that's eyeball reflective light. Has not much to do with heat. And I found that out real quick. All you have to do is put your hand on the back of that plate and you're going to burn your hand. Just like the hood of your car, if you, I was talking to the military one time and I went out and I said, it was in Tucson, and I said, I walked in, it's 112 ambient today. I said, I see some white cars out there. And I said, so everybody that has said that white paint reflects heat. And I said, well, I need somebody to go out there to that white car with me. When we get out there, I want you to drop your pants down, sit your bare butt on that white car, and in a low, calm voice, tell me how cool it is. And nobody took me up on that. And I said, that's what I'm talking about. You have density, and white paint doesn't really block that IR or that other heat from radiating into that thing. 70% is light, visual light. What's the heat? It didn't block a whole lot of heat. Blocks some. And they may be only a difference of 30 degree F, which is about 8 or so, 7.5. C, difference between a black car and a white car on a hot day and putting your hand on it. So not a great big difference right there, because the white paint allowed something to go through and heat it up. And once that metal is hot, it's hot. So in the whole process of this, I was taking these ceramic compounds, mixing them into this white paint, putting it on that plate, turn the lamp on, and how much heat came through. Well, all 17 of the #1 ceramic compounds that were supposed to block heat didn't block heat. And I thought, well, wait a minute. So I called them back. I said, what's this? And they said, well, we never put it in a paint, mixed it with other materials, and in a water-based, and then you put it and it dries out, but it's always been measured in a dry state all by itself. I said, well, that's not a paint. And you can't take something and it all by itself, it's a powder. You got to put it in something to hold it on there. And it's, well, you'll have to do the research and find out which ones work. That's how it all got started. Because I didn't intend on doing that. I thought, tell me how to do this. I want to become wealthy in 6 months and we're good. We're good. No, that ain't the way it's going to work. So then I said, all right. So I had my system for checking it, which was trial and error. This is going to be how it is. Either it works or it doesn't work. And I really didn't care. Just show me something that's going to work. And because I had already found out reflective coatings or paints at the time, they didn't do anything. They had visual light bounce, and it might have made a 2 or 3 degree difference on the inside. And it's like, that's nothing. You can't, I don't want to sell that. So it's like, okay, so I started asking NASA and their different offices from California over to Ames and the rest of them, different engineers over a 6-year period from 88 to 95 or 89 to 95, and about ceramic compounds. And I mean, we went to the rare earths back and forth, and we covered a lot of compounds during that time frame. And I have to say luck had a big hand in this, because one of the MIT guys, engineers, I knew more about ceramics than he did, about just ceramic compounds and what they look like, what they did, because there's not a book on that. And there's maybe a half a chapter on ceramics and things like this, but who has gone through trial and error on 4,000 compounds and could tell you what they were, how they would respond to heat? It's not there. So I started in, and as I went through all these compounds, they just failure. And then I would run across, and I even went through 20 manufacturers of beads, hollow spheres, 20. And each of those 20 manufacturers may have had 8 to 10 different kinds of beads and different sizes. I went through all of them because I thought I had heard, they had told me, oh yeah, beads are good. Well, that's what you need. And it's like, okay, if I had $1 for every time I was told that, I would be a wealthy person. You've heard that story. All right, well, I'm the same. And it's like, my God, I found out that's not true. There's certain beads and there's certain compounds at a certain size. And that micron size is going to affect that heat wave. Well, which compound is it? Trial and error is the only way you're going to find it. And crystalline structure is part of that. Hey, what do you mean crystalline structure? Well, that's how it's designed. How does it catch heat and how does it throw it? Or is it just a smooth surface that's going to load and over time it loads in like a bead and then comes on through? So a bead is good, but it's got to have help in order to make it complete the process of blocking heat. So you got crystalline structure. That's not in a tech sheet on any of the raw materials. What's a crystalline structure? Well, I don't know. And so with this MIT guy, I was telling him that, and he said, well, wait a minute. You're nothing more than a cook. And I thought about it for a minute, and I thought, you know, you're exactly right. I'm nothing but a cook. Because I can hold a raw material in my hand, a powder, and tell you whether or not it'll probably work or not. From the feel of it, from the density, from the feel being the crystalline structures and how it's made. But I can look at it. Well, that's just a cook. Is that scientific? If you want to go back to the very beginning of engineering and chemistry and everything, Leonardo and those guys, they were pseudo people getting into this thing. They didn't know what they was doing, so they were doing all of this experimenting to come to it. And so alchemist is what they call. So I'll just consider myself an alchemist. Because what's alchemy? That's when you're putting things together to make something else work. Okay, that's what this is all about. So in alchemy, you don't go with the books. The books only know what they know. And maybe they're 10 years old. Well, what good's that for me? I need to know what's now, what's current now, and what works now. Not 10 years ago, now. And so NASA decided this is good. So they're going to help me, supply me, tell me where to find it, raw materials. So around the world, all the way from Dead Sea to you name it, Russia and every place else, and Asia, across Asia and South America. And all the way to Brazil, chasing down some compounds there that was used back in the old days when things worked and everybody's forgotten why they worked. Well, I go back and study those things, because why did it work? And why don't we continue working it? Well, it got dead, and we went off onto something new, and they forgot about it. Well, I go back and study those things and try to figure out what it was, bring it in and try it out. Most of the time, it doesn't work. And like I say, 12 work out of 4,000. I'm used to failure. That's not a problem. So in this 6-year period, until from about 89 to 95, we're working on this thing, and they're supplying, and I'm doing the testing. Then we get it to work. They do their own testing. We've got the NASA that actually tested. So any and all of these people, and I have to kind of grin, it was irritating at first, and now it's not, it's just kind of a grin. But we're NASA technology and we're this. They only say that because they can spell it. It's only 4 letters. So it's easy to spell and they can use it. But we, on the other hand, have been there. NASA has tested Super Therm. They understand what it can do. And so in 1995, they had their big conference, technology conference in Chicago. And so they invited me to speak on Super Therm because it was a joint venture of putting this thing together. And so there was 400 or 500 engineers there worldwide that came in. And then luckily for me, I had an hour, but then the next hour the guy didn't show up, so I used 2 hours. And then the next guy finally showed up, so I finished in the hallway outside the rooms there, the conference rooms, to the people who wanted to know a little bit more about it. But it was how it worked, why it worked. And even aeronautical engineers that I was talking to with D. Howard down in San Antonio, in blocking heat on a reverse thruster with a water-based coating, we did it. It didn't quite get to the level they wanted, but it blocked it. And they were trying to change from titanium to something cheaper and just reduce the cost and the weight. And so all of them were going, ceramics. You know, what is this? And so from that point, we had found enough that it was working. If I went out and coated a metal roof, then all of a sudden we were within 2 to 3 degrees of ambient temperature. On a, say, a 38 C day or 90-degree day, Fahrenheit, and come down, and that roof could get to be about 80 C or something like that, 160 F. But if I coated it, then all of a sudden the emissivity, reflectivity of the ceramics that I used, and I came down to 4 ceramics in the Super Therm, that one is a bead, but a particular size. And if you ask me exactly why does that one work over the other, then I'm not going to have to sit here and act like some kind of smarty aleck, because I don't know. But at that particular size and that particular makeup of that bead works out of all of them that I tested. So it's in there. All right, then the other 3 are these crystalline structure type materials that's kind of like little crystal fingers on them. And they're overcoated with another ceramic compound in the heating process that makes it go to a high temperature or higher temperature and withstand a blowtorch. And later on, I'll do that for you. And if I burn my hand off, well, that'll just be part of it. But anyway, hopefully it works again. But those are in there. Then I was working with the Germans over in Germany, and they're having a discussion about IR. And so they had a different reason for the discussion, and I'm sitting there, I'm nothing more than a sponge. And I'm soaking up what they're saying about how you block IR radiation waves. And it had to be a certain material at a certain micron size. And let me stop for a minute. It's never been a nano material. Now, I wish there was, because I wanted to make a clear coating that would block heat. It has to be nano so you can't see it, it's clear. And anybody that makes up a coating and it's not clear and they call it nano, that's a little on the stupid side, mainly because what is a nano? 1/1000th of a meter in size. You can't see it. It's like, okay, maybe you could, but it's like welding and the smoke that comes off, those are nanos. They're floating around. You got to catch. I had a package sent to me from China one time. This is nano material. It weighed about 5 pounds. It's about like this, about that thick. And I thought, yeah, right. Cut into it, and it's a white powder. I can see it. It's not floating anywhere. It's not nano. So the people that get into this nano thing, that's just a catchphrase, and you don't want to go for that, because the nano is very small. You can't see it. I wished I could find that nano. I'm been looking for years, to make a clear coat that would do the same thing. Now you can make particles in there, like in photographic film that they use in the silver parts of that. You can put it into it and it helps to reflect, but it's not completely nano, because you can see some kind of a silvery sheen to it. And I want a clear coat, which would be nano. I'm still looking. But this nano buzzword, if you can see it, it's not nano. So, or at least the smoke You can see some smoke. If you take that smoke and put it into a coating, it's a little hard to do sometimes, but it's to get it in there. But that's what you're talking about. But what they got into was it had to be a certain material for blocking IR. IR is 57% of the heat to anywhere from 54 to 57% of the heat that comes from the sun, radiation. That's the main one you better worry about. If I got a white paint, it blocks all the heat. No, no, no. Which heat do you block and why? That's the question. So I got it into they said, well, it's got to be a certain micron size to match up with a wave, and it's got to be a certain material that can do that with a crystalline structure to do that. And so I'm sitting there listening to them, and when it's all said and done, I get back with them and I said, well, I need some smaller than that, the size you said, and larger than that, because my brain is telling me if it's that good, the larger I can get it in there and it may work, or smaller, it's denser together and it'll work even better. Well, neither one of them did. What they said, they knew what they was talking about, and I thought, it's got to be this size and it's got to be this level in there, and it will then catch that wave and block it. And whether it be energy waves in heat or sound, because we've got it where it'll block sound, and we did all the ASTM testing on sound to show that and prove it. And so heat and sound ride in the same car on these waves that come in. And so if it blocks heat effectively, like we got, it'll block sound, and we proved that with testing. And so as we came through this thing, it was you had to get all of these pieces put together in the coating. So then after 1995, I was told that you need to get into some universities, have them do some testing themselves. So I did, and they tested it and said, well, it brought the 367 BTUs down to 3.99 coming through the coating film on a metal plate to the other side. The metal plate by itself, you had 367, you got 367 on the back side. So, well, we knew it worked. And then they gave me some letters that said it worked. And so then the next year I went to another lab, and he said, well, you know, he gave me an RE type letter, and I said, okay, I'm off and running. Then in 2002, I heard that some coating company, white paint, had gotten in trouble for stating how they insulated and using certain terms that was used at that time. And I thought, well, wait a minute, I've come all the way through NASA, and we've never been worried about, this entire time, worried about the insulation terms used out there. And I thought, I'm just, you know, in the NASA, everything they do is heat blocking. It doesn't have these terms, like an R or whatever. But I said, okay, who's controlling this? So I called Washington, D.C., got a hold of the agency that does this. I said, do you have testing on this to prove this thing? Yeah. I said, well, I don't think anybody in the coating business knows about this. I said, what is it? So they told me where to find it on the website and all this. So I went to a website, pulled it all off. It's a rule for advertising. And so I followed, there's reflective, and I followed all the testing and performed it all in 2002. And completed it. Now, I completed some other steps of it in 2006. And so the emissivity part of it. And after that, I thought, well, you know, engineering groups around the world, they only know one thing. What's that term for insulation? And how much you got in that? And I said, that term that you use for insulation, the R, is how long it takes for a material to reach heat flux. What do you mean by that? Loading. It loads the heat that was coming to it. Now it comes through the other side. And that's calculated. I said, we're not made that way. To me, that's not insulation. So what do you mean? What I'm trying to do is tell you that surface, I want to coat it, and when that heat comes in here, I want to repel it off where it doesn't load into that surface and come to the inside. And I know I was talking to some architectural engineers in Miami-Dade County for the schools. And they sat there and listened. I didn't know who they were, but they were sitting there listening very intently, but looked like there's going to, they had some swords with them. They were going to cut me up later. And finally I said, you guys agree with what I've just said? And they said, well, not necessarily. And I said, okay, well, tell me why. He said, well, we've heard this all before, that you can throw off the heat and everything, but most of it comes through, and we have to have your standard insulation materials on the inside. And I said, and that you can't have that symbol with the standard insulation materials, and so you can't block conduction. And I said, okay, let me take that point right there and let's discuss something real quick. What you're talking about is conduction, load, and conducting all of it until it hits heat flux, maybe in the middle of the day. If it's really hot, it's already filled up with heat. So why do they say, gosh, it's not working? You need to add more thickness. Well, it's a hell of a sales technique, but wait a minute, it's loading. And you're telling me you'd rather have this number of how fast it loads and hits heat flux and add more in there until it doesn't. You can get to the end of the day, maybe. And then when the night rolls around, you go, oh, we're good to go. All of that's loaded with all of that heat. So a lot of that heat is going to go to cool because that's physics. So it's going to travel to the inside until about midnight or so. And especially if you're in some kind of a mobile home, trailer or something like this, it's only got about that much. And you can burn the top of your head standing up in the thing. And I said, okay, that's what you're talking about, is conduction. What if I could tell you, and I can prove it from testing, from NASA to the others, in certified labs, that I can keep that surface within about 2 or 3 degrees of ambient temperature. So instead of it going from, on a 90-degree day or 38 C, instead of it going to about 168 or something like this, F, or about 80 to 90 C, I can keep it within 1 to 2 degrees of the ambient temperature. Did I or did I not block the heat load and reduce the amount of heat available to transfer? And I give it to them because they were locked in on conduction and all this, but they thought about it for a minute and they said, so if you reduce from 38 C, normally it gets about 90 C on that roof. You block that down to about 39 C, you've reduced the amount of heat available to load and transfer. Okay, that means something. That's all I'm talking about. I don't want to be like standard insulation. I'm not going to absorb the heat and load it, so I have to have thickness to continue put thickness in to prevent the load at the end of the day. Now, is that loaded? Yes. And when the sun goes down, some of that's going to continue to go to the cool where the air conditioning is. That's physics. We can't argue that. Until midnight or something like that. And then the air conditioner never cycles until you get into 2 o'clock in the morning. I said, or I've coated that. We've blocked it down to about 2 degrees of ambient. It didn't load all that. Sun goes down, we're cool. And it cycles. That's what I'm talking about. And that's the premise of the entire program that I came from NASA with, is that we're not interested in loading anything. That's not insulation to us. What we're talking about is blocking the loading of the heat to start with. The initial load, no. If you load it, then you got to deal with it. Don't load it. That makes sense. So that's how then we went from, in 2002, I got a hold of a local DOE expert down in Florida. And he says, when I first called him, he actually cussed me out on the phone because I said ceramics. I've heard of all you guys, your ceramics, and I thought, oh my God, here it comes. The guys before me screwed it all up. Now I have to just deal with this. And I said, yes, sir, I agree with everything you just said. And not maybe all the names you call me, but everything you just said. And I said, but this is different, and I'll tell you why. There's 3 different radiation waves from the sun, and I have studied and found the ceramic compounds that could block those radiation waves. And I said, all of a sudden there's silence on the other end. And I thought, did he hang up? And I thought, and I said, you still there? And he said, yes. He said, you finally said something that made some sense. I said, well, thank you. And I said, all I want you to do is test it. If you don't think it's any good at all, just let me know, and it'll save me a lot of heartache and time and trouble and expense. He said, send it down here, and I don't want you calling me. Yes, sir. So I sent it down to him, and he went through some testing. Well, I never heard back from him for, I don't know, a month and a half. So finally I thought, I got to call him. So I picked up the phone, called him, and I said, yes, sir, I'm just checking on that testing if you got some testing. He said, well, you know, we did. I painted half of a roof on this house down there, and I was doing monitoring on the half not painted and the half coated with your coating. He said, you got about a 2-year payback on that, and it saved 3% on the energy, I believe he said, that brought through on that attic. And I wanted to say, well, if you'd have painted all of it, we would have, because the heat over here was just, it goes to cool. So where I painted it, that heat was drifting over here underneath the cooler part of the roof. And he said, who's doing the test, me or you? And I said, yes, sir. Well, that's okay. You know, and he made up this chart and showed how well it did, how much carbon it reduced, power plants, yada, yada. And I said, okay. And he said, but this is just Florida. I said, yes, sir. And I said, so what do you want to do? He says, well, you pay, but we're going to have to do this in 2 or 3 different locations in the United States to verify the results. And I said, fine, I'm into this, let's do it. And I said, where do you want to go? He said, Denver, Colorado, and LaPorte, Texas. And I said, okay. And so we did test on all those places. And in Denver, it was cloudy all day long, and he made me build 2 identical buildings, one coated with a commercial reflective coating, and then one of them coated with Super Therm. Except this one over here was coated, it was built and then coated with a Super Therm. Mine, he said, you coat each individual board and then we'll build the house. I said, why is that? He said, I've already seen how this coating works. It seals as it goes, and it seals off moisture and humidity and stuff like this, and that's unfair. I mean, you mean to the white coating? Yes. Okay, so we had to coat each individual board, hardy board, before it was built and put it together and out there. Then he did video, he did 5,000 points of testing in a 24-hour period. I mean, he was serious about this stuff. And then he said he had a video on it, and it was cloudy the 24 hours that we were doing our test. but we still beat everything and even the standard materials by 30%. And he says, that stuff's pretty good. This is the second test. Third test going to be LaPorte, Texas, and I'm doing it on some containers, shipping containers, because now they're using them for building homes. That's fine with me. And so he did, that was in 2002, 2004, and the last one was 2006. So then I said, okay, well, that pretty well verifies what we've been saying. And he said, yes. On his third report, he said, this verifies your Energy Star verification, because I had submitted Super Therm to testing for Energy Star, like your refrigerators and things like this, for saying, well, you had that for roof coating too. And it's the beginning of how it started and then the end of how much reflective it would throw off heat and things. Except I didn't particularly like the test because they didn't include all the IR radiation into that test. I asked in the beginning and they said, well, it is limited. And that's the reason why later I went to Russia at the Russian Academy of Sciences and Japan at the Standards Construction Sciences laboratories and had testing done. They're a little bit more advanced than we are in actual doing all the radiations, and got an average of 95 is what we've been saying. But anyway, we got that, and it has an Energy Star rating. He said, so you certified that. And I said, thank you very much. And so then I went, and in this particular rule that I got from out of Washington, on page 15, last paragraph, it says specifically you use DOE regular, federal DOE, Department of Energy, and or local energy experts to verify things. So that's what I was doing. Well, he did it, and geographic was one thing nobody does. But he demanded, and we did 3 geographic locations to verify its performance. But then in 2010, I didn't know this at the time, but the Federal Department of Energy has a weatherization program. And they were doing low-income housing down in Jacksonville, Florida. So they had, through a contractor, get some product, Super Therm, take it down and coat this one house, this trailer. And so this elderly woman lived there. And so and I didn't see this, I didn't know what was going on. I didn't see the report until a couple of years later. And I found out that they had done it. And in their statements in the whole program, they stated, well, we're checking the advertised statements that Superior Products is making about Super Therm. And I went, oh crap. Okay, if I'd have known that, I'd have been nervous. But they went in and they had a roof that was not coated, and it was on an 85, I think an 85 F day, which is about around 40 something, 38, 36 C, something like that. And that's right, about 34, 36 C is an 85 degree day. And the roof, uncoated roof, metal, was 160, I believe it was 165, and F, and that's about an 80-something% C. And then they had taken a competitive commercial industrial reflective coating, touted to be the very best, and coated a roof. And it was 125 F, and that's about 60-something, and C. And I said, okay, and then I read ours. And on an 85 degree day, ours was 86 degrees F, just 1 degree over ambient. So with the C, if it was like 36, it'd be a 37 or less. It just went up 1 degree. But it made, now this is the report, it made a 10 degree difference F, which is about 3 degrees C, just in relationship, difference inside the home. And so they thought, okay, you have met, you had if you go from the 165 down to the 86, 1 degree over ambient, you're talking about a 99%, just mathematically, 99% reduction in heat load into that surface. And if you get into engineering and everything, they'll argue that, but it's just math. So I'm going to go with just the math. 99% reduction in that heat load. And so when it made a 10.2 average temperature drop inside that home, then the auditors for the Department of Energy came back later and talked to the lady that was there, and she says, I never turned on my air conditioning, because she says now it's about 70 degrees, 28 C, whatever it is, inside, and she says, I got some fans and I like it, so I don't use air conditioning. So and that was the Department of Energy in 2010. Since that time, we're always out there. We'll throw it and see what happens, but we had the U.S. Air Force, and he wound up being a lieutenant colonel. But the captain at the time said he was the energy man at Tucson. And so he said, well, we're going to coat some buildings out here, but we got to make it a light tan instead of white. And we got to do some different things out here with it. And I said, okay. And so then I was, some representative was kicked off, and I was invited out in his place to do the talk. And that's where the guy with the set your bare butt on that car expression came from. And then we all went out to see they had coated a double wide on the base, Davis-Monthan Air Base in Tucson. And that's where they store a lot of aircraft and things like this out there. And so we went out to check it. Well, I hadn't seen the building. I didn't know where it was. I hadn't seen it since they coated it. I hadn't taken any readings, but I had my little R gun with me. And so I'm looking for it while they're talking about other things. And I find it, and there's some people standing around, and one of them happened to be another coating person that was there doing some kind of a frying pan showing how good his coating was. And I don't know what you're doing, but the frying pan is, I guess, looks good. It doesn't work in the real world, but it looks good. And anyway, I said, no, I'm just out here to show you how it really works. Anyway, so I get over there to this building. Well, it was 113, it was 112 to 113 ambient temperature. So I get over to this building, and so I shoot it, and it's within about a degree or so of ambient. And I thought, okay. And so I found, and then this guy that had the other coating, he was standing there, and he says, well, that, anything is like that. And there's a bunch of people standing around, and I thought, okay, dude. So I found a metal piece that was close by, and so I went over and shot it, and it was like 200 degrees F. And so he said, well, your gun's no good. And I said, well, you got a gun? Yeah, I brought my gun. So he shot it, and it was 200, whatever mine said was, And I said, well, shoot this over here. And he was kind of hesitating there for a minute, but finally he shot it. It was about 1 degree over ambient. And then he just left. And when we got back, he had cleared out his space and left completely because he couldn't do that. But my whole thing was, what's the temperature on the inside of the building? Because then I was told to shut off the air conditioning to this double wide. It has no standard insulation in the attic. And it's been sitting here 3 days at 112 degrees. And I'm going, oh crap. I don't know. I really don't know what this is going to be. And so they finally said, they announced, okay, now we're taking a look at this insulation coating, they called it, instead of by name, Super Therm. And so we got in there. Well, I was one of the ones that elbowed my way in first and started shooting around trying to figure out what's the temperature in here. And when we got inside, it's like It's like 86 degrees Fahrenheit. And I thought, 112, 200 would have been on any metal surface. It should have been about 160 something degrees inside this thing. It's 80, I think it's 86. And everybody's standing in this thing with the doors open now, so it's getting a little warmer. And they're saying, is there insulation in it? And I could reach up and hit the drop roof, and I lifted up and said, no, there's nothing up there. This is just Super Therm on top and on the sides of this building, and no air conditioning running, and it's only 86. And they go, all right, point is proven. And I thought, of course, I went like this, like, oh yeah, I knew it would be that way, you know. And it was like, oh my God. But so I've had it tested whether in circumstances, in real world circumstances, whether I wasn't there. I didn't have anything to do with it, but I wanted the coating to talk for itself. Sell itself, or if you can't, then you're not a good coating. If you can't sell yourself. And that's how all these coatings are made. You either sell yourself, because I can make you, and I got the science behind the making, but you got to get out there and show your stuff as a coating. And so it has. And then from the progression of that has been that we went through the military, we've gone through airports in Vegas, and they call it jetways. When you leave the terminal and you're walking down that jetway to get on an airplane, you can nearly die of a heat stroke in some of these really hot areas. And we're coating all of those so that you can get from the terminal into the airplane and you really don't feel much. It's a big deal. And so we're doing that, and we're starting to do airports and things like this, because as the guy, this is the kind of thing I love. The maintenance over all of the guy, over all of this for the airport, he had several come out here, competitors come out there, and they would build it up and then build up a little bit more and build up a little bit more, trying to get it to work. And we walked in, and I didn't know that. And I walked in and said, it only takes 10 mils or 250 microns. Really? I've already seen all this other crap, and it's like, yeah, right, okay, we'll see. Well, I put it on there, and that's what it works at. If you put it on thicker, it really doesn't do you much good. It's designed to work at 10 mils or 250 microns. If you build it up, I'll sell you the coating, but it ain't doing that much more, okay? It's designed to do that, to work that way. You don't build it up. Not like the thick coatings. And it's like, and then it just beat the socks off of everybody out there within 2 or 3 degrees of ambient temperature, which just reduced the inside of that temperature inside those walkways, jetways, tremendously. So he's one of these guys that says, well, hell, it works. We're going to use it. Okay. That's it. And so it's, again, we don't go back to that standard insulation terminology. It blocks heat load. That's the point. That is the point. So we have gone all the way through the oil tanks and the oil fields and gasoline tanks. And the other big deal is LNG. They have flare-offs. And it's dangerous, because I was standing in some plants in Saudi, and they're flaring off, but not all that's being burnt, so it's kind of coming off tank and landing on the ground around. You may be ankle deep in natural gas. And it's if you got a nice wind, you're good. If there's no wind at all, you could be in trouble. And so it wasn't the engineers that were looking for insulation and everything. They didn't care. They're used to having so much loss, a certain amount of loss and flaring off and such and so forth. It was the safety engineers that came around and said, hang on, it'll do what? We want to coat a tank. And we did. It cut out the flaring, reduced the PSI on that thing to where they didn't have to use a flare, and maintained it. So the safety engineers is the one that dictated that, and we proved that it saved the loss of all that natural gas. And so it did that. Now we're working in the Middle East on a bunch of other things. South Africa the same way, with our guy there. And so it's the coatings, like I say, go out there and do what they do. Now, in the ceramic side of this thing, we have made the thin coat and then the thick coat. On top of that is I've worked on for years, designing a fire coating that can go on maybe at a, and we'll do the testing, we're with UL doing a 1709. I will not do the ASTM E119 because that's a slow temperature start and comes up to 1800 to 2000 degrees finally. And that's not what we're interested in industrial areas. Industrial areas, if you have an explosion, you're at 2000 degrees just like that. So this UL 1709 is in 5 seconds, you're at 2000 degrees. Spigots, 12 spigots on each wall, all four walls, hitting the column that's been coated. Well, it's just hell on wheels is what it is, because you look in the window, you don't see anything but fire. And that's what I'm making now. And we've got plates we've finished with. I've improved it. And this is the third or fourth time I've gone back to UL to spend all that money to do a test to find out I'm not good enough yet. And what I'm doing is I'm taking 4 4-foot columns of I-beams called stubs. And I can then bring this in and coat each of those with 12 millimeter, half inch, 750 mil or 18 millimeter, then a 25 millimeter or 1 inch, and then a 37 millimeter or 1.5 inches. And burn them all at the same time. They've been probed out, and figure out where we're at and what our thickness is to replace all that concrete that you put around I-beams that's heavy. These 2 5/8 inch wall boards, you got to put 2 on each side to get a 2-hour fire rating. All this stuff is, we just want to spray it on, water-based coating, spray it on, and it work. And so that's the ceramics, and I've never stopped dealing with ceramics. I study them every day, bring them in. It's never stopped in 34 years. So we will develop new coatings later on based on what we already know. Again, I'm nothing more than a cook, and I love it. So we will develop things as we go along that'll be even better than what we have now. But the coatings speak for themselves, and they do their own selling. And so we just get them out there and people see what they do. So that's more or less the history to this point. Thank you very much.